.3.1, talking about quadratic functions. Okay, you know a lot of this. Okay, but the way that you know it might be kind of like I've seen this, I've seen somebody do this, and now I can do it. That kind of mentality. You're kind of going through the steps, just kind of plug and chug, and just work everything out and get results. My hope now is that when we look at quadratics, that we understand after today and after Tuesday, that we understand that when we look at it, there might be 3, 4, 5 different approaches to gain the adequate information to actually discuss the function and ultimately, hopefully, graph the function. Okay, and I want to try to give you different avenues to do that. Okay, you already know a lot of this, but like I said, I want us to kind of understand how we can look at these functions from different perspectives and still gain the same information. Okay, because question number 1 on the homework might ask me to use perspective A. Question number 2 might be set up to where perspective B makes it a little bit more efficient, a little bit easier. Question 3 might be perspective C to gain the same exact information. So I could have gone perspective A on all 3 of them, but knowing 3 different ways of doing a similar type of problem might allow me to be quicker. Does that make sense? Yeah. So that's kind of hopefully the understanding that we gain from this. We talked about this previously. Okay, so the way this, I don't necessarily like how this textbook is structured, is that in chapter 1 they do a little bit of quadratic function review. We did the projectile questions with we're launching a ball or whatever, and we needed some of this stuff when we did that. In my opinion, it feels like we're kind of we talked about quadratics maybe 4 or 5 weeks ago for a couple days, and then 4 or 5 weeks go by, and we're going to start talking about them again. I wish we would have just done that all at one time, but it's just the way things are structured. It's the way Rhodes structured things. So we have talked about this before. This is the general form for any polynomial. Okay. It says a sub n, and the a sub n's are the a sub n minus 1 and the a sub n minus 2, the a sub 1. Those are just coefficients for your individual polynomial terms. Okay. The n's as subscripts there just are able to allow us to link the a sub n goes with the x to the n, right? It tells me that that's the coefficient that goes with the x to the n. This is the coefficient that goes with that term x to the n minus 1. Okay. So these are just allowing me to link a link between the coefficient and the actual variable exponent. Okay. So I want to try to get these subscripts there. There's no algebra being done with it. They're identifiers. Okay. It says a sub n cannot be 0. You think about this. So let's say if this thing is a quadratic, but a sub n, which would be my x squared term, my x squared coefficient, if it was 0, 0x squared disappears, right? Okay. So then it would leave me with either a linear function or a constant function, which is still linear, which is no longer than the quadratic that I'm looking for. So it depreciates it if a sub n is 0. So we don't want that to happen. We want to make sure that our a sub n is a non-zero number. Those ellipses mean that pattern goes on forever. So here's the idea. We're going to learn stuff about quadratics, specifically quadratics. We'll learn stuff specifically about cubics, things specifically about quartics. So these are 3rd degree, 4th degree, 5th degree quintics, and so forth. So if I give you something like x to the 13th, you will know how to do that, even though we never specifically talked about x to the 13th in class. You'll be able to do x to the 13th because you know what x cubed looks like. Does that make sense? So what we learn here is our first kind of cluster of polynomial functions: quadratics, cubics, quintics, quartics and maybe quintics. And what we learn from those then have carryover into an infinite number of other polynomial functions. Okay? So my hope is that we're not learning, this is just how I do quadratics. This is just how I do cubics. Because the information that we gain can be then transferred over to other degree of functions. Okay? When we talk about the degree of a function, okay, we are talking about, we're identifying the largest exponent. Okay, the largest exponent for our variable terms is going to identify our degree. So if we look at f of x equals...
that on Apple Watch.
Because you're stupid.
Hey, did anyone have a motion? I was going to ask, but I didn't want to interrupt you.
So weird. So, a quadratic function is a degree too. So when we talk about the degree, we're always looking for the greatest exponent. Okay. Polynomial functions. If we go back to our rule prior, like the a sub n to the x to the n plus a sub n minus 1, x to the n minus 1, we have to have integer exponents, positive integer exponents. Okay. Otherwise, we get rational functions. Okay, so that's something to think about. So everything, you're never going to see a negative exponent in your polynomial functions. Okay, so there's going to be positive values as your exponents. Here, obviously, we don't want a to be 0. This is the idea. If a was 0, this would not be quadratic, right? If a was 0, that term right there where my cursor is would disappear, and I'm left with bx plus c, which is just a linear function, right? That's our quadratic. Now, there's a little terminology issue with some textbooks. Scroll down to this here. Okay. There's a terminology difference from textbook to textbook. Meaning, I've got like 30 textbooks back there that deal with college algebra, pre-calculus, that kind of stuff. If we were to take those 30 of them, half of them are going to say this. The other half are going to say what I'm going to teach it as. Okay, I want you to see this because this is how WebAssign uses it. But I think it's not a great set of terminology. And this is the way I'm going to teach it. And the reason I teach it this way is because you've learned it this way in Algebra 2. We call this format here that we're going to try to generate, that right there, we call that vertex form. Your textbook calls it standard form. That make sense? Okay, I'm going to call it vertex form, one, because you learned it that way last year. But the second one, the second reason, and maybe the more important reason, is that those two things right there actually tell me what the vertex is. Okay, if we understand our transformations, when I subtract h from x before I run it through the power of 2, before I do that parent function to it, isn't that going to move it horizontally? And then when I add something to the end of the entire function, doesn't that move it vertically? So if I know my parent function x squared has a vertex at 0, 0, that h is going to take that 0, 0 and move it left or right, and then that k is going to take that 0, 0 and move it up or down. So it's going to put my 0, 0, my vertex of my parent function, at a new position, and I'll be able to determine what that new position is pretty easily. Yes?
Do we have a midterm?
No, we'll have a final. No.
Okay. So, and is like the h like the opposite? Or?
Yes. Yeah. We'll talk about that in a minute. So I'm going to call that form there vertex form. The one above it, where it's ax squared plus bx plus c, I'm going to either call that polynomial form, or I'll call that standard form. Okay. So other textbooks, this textbook flips it. Okay, they call a times x minus h squared plus k. They call that standard form. And ax squared plus bx plus c. I have to look and see what they call that. I think they call it polynomial form. Other textbooks call the top one standard form and the bottom one vertex form, which I think that's the more appropriate way of talking about it, in my opinion. Okay. If you get confused with that, just remember there's only two forms that I can write a quadratic. Either that top form or the bottom one. Does that make sense? If they give me the top one and they say, write this in another form, then I have to put it in the bottom form. Or if they give me the bottom form and they say, write this in a different form, then that means I have to convert it into the top one. Does that make sense? It's one or the other. So hopefully that's not a big deal. But what's nice about this, so like I was saying, if I've got my x squared, so let's just think about, we'll just draw it on here. If I just think about my original parent function x squared, okay, we talked with transformations in the last chapter. If I take x squared, and before I square the x, if I subtract h from it, and then square it, isn't that going to move that thing to right there? Make sense? Okay, so if I said x minus 3 squared, it would move it to the right 3 units. If I said x minus 5 squared, it'd move it to the right 5 units, correct? And if I add some value to it, k, at the end, that's going to add to my y. So it's going to shift my y k units up. So it takes my parent function, ordered pair 0, 0, and it moves it to right there, which is now the new vertex of that red parabola, right? Okay, so that's the idea of this form, this vertex form, being able to gain information from it. Now, Blaise asked, if I look at this, it said f of x is equal to a times x minus h squared plus k. Okay, so let's put some numbers in here. I don't care what a is. If I go x minus 3 squared plus 5, okay, what is the actual vertex? If I understand transformations, it's taking this thing, x squared, and moving it which direction first? To the right. So the x value has to be positive. Okay? Now this positive 5 is going to move it to up, right? So the idea is that I'm not concerned about what the sign is in here for that 3. If it's negative, I'm just taking the 3. Okay? Let me ask you this question. If I have f of x equals a, let's go x plus 4 squared plus 5, where's that plus 4 taking my 0, 0? It's going to move my function to negative 4, right, in the x direction? And then 5. Now here's the reason. Isn't a times that quantity the same thing as this? Does that make sense? Subtracting a negative. So if I'm able to keep that negative right there, like I am in my original, come back up here, well, that was a minus right there, correct? Okay. If I'm able to keep that, then it shows me what that coordinate is of the x value directly. So kind of makes sense? Okay. So that's the idea of just knowing that addition is subtracting the opposite. Okay. But that gives me my vertex. Okay. I'm able to quickly determine my vertex from that information. Now the rest of this blue box kind of talks about the a value out in front. Okay. If this a value right here, come on. So this a value right there, or that one right there, which they're going to be the same. If it's positive, it's concave up, which is that graph on the left. If it's a negative, it's concave down. Okay? Just kind of think about the one on the left. Am I going to have any x-intercepts on that one on the left? Nope. Okay? So if I go through and I find the fact that my graph is concave up, and my vertex is in the first quadrant, I don't have any x-intercepts. So in regards to graphing this thing, I won't even worry about that. Does that make sense? Okay. If I look at the one on the right, okay, I know my quadrant, or my vertex in quadrant 1. Now I know A was negative, so it's concave down. So visually I'm thinking, okay, yeah, I'm going to have x-intercepts. And now that would lead me to going through the math to find those. Does that make sense? The idea is, can we give ourselves an understanding of what the graph is going to look like prior to doing any algebra, because that's going to allow me to make decisions about what algebra I need to do and what algebra I don't need to do. Now, one on the left, I don't need to do x-intercept algebra because they don't exist. I would get I's in my discriminant. Wow. Okay. This is fun.
I think it's fun.
All right, thanks. All right, so we're gonna do one of these, okay, and kind of talk about the overall procedure and purpose of this. Okay, so we look at 2x squared minus 12x plus 13. That's polynomial or standard form. Okay, and they like to present a lot of things like that. Okay, most of our questions throughout the rest of the year, you get the calculus. Most of your questions are presented in that form. But I might need to do something to that to understand what the graph looks like. Okay? If I give you that and tell you to graph that, your best, without a calculator or anything like that, your best guess is probably just start picking x values, right? Maybe you find the y-intercepts. Maybe you find the x-intercepts. But then to fill in the missing points, maybe you just start choosing plots in the table and evaluate. Not really the best method in regards to efficiency. So what we want to do is we want to take that function and we're going to see if we can put it into vertex form. Okay? This is something that you've been doing. You've been doing this since Algebra 1. Okay? We're going to complete the square on that thing. Okay? Now, here's the thing. We do completing the square enough that it shouldn't be something that we really struggle with. Okay? And once you complete the square, it actually generates, if you remember, completing the square is the same thing as what formula? Quadratic formula. So when I complete the square on this, it's going to put it in vertex form. That's awesome because it puts it in vertex form, tells me the vertex, but also gets me to a position, if it's the same as the quadratic formula, doesn't it get me the position to be able to find the x-intercepts pretty quickly? Yeah. Okay. So if I were to add, before doing this, before any discussion today, and I asked you to find the x-intercepts, you would probably try to factor this AC method or maybe using the quadratic formula. Hopefully today, because I'm going to ask you to graph this, find the vertex and all that kind of stuff, you understand that when you do that, you do a lot of the work for finding the x-intercepts. Okay? So this is how we're going to do this. We're going to say f of x is equal to 2x squared minus 12x plus 13. At the onset, we know it's parabolic. We know it should be concave up. Okay? But that's really all we know, right?
Yeah.
Okay? I don't know the vertex. I don't know how this thing's been shifted left, right, up, down, anything like that, stretched. Okay? It's not until I put it into vertex form that I can figure that stuff out. Okay? Maybe you have some intuitive ideas of what's going to happen, but once we put it in the vertex form, you're going to absolutely know what's going on. So the first thing we're going to do is complete the square. There's two options. You can either divide everything by your leading term, that coefficient, or you can subtract c from both sides first, or you can do them both at the same time. Okay, so I'm doing it at the same time. You guys agree that if I divide everything by 2, that's going to give me f of x over 2. I'm going to subtract 13 from both sides, so it gives me negative 13 halves. Divide 2x squared by 2. Divide 12 by 2. That's moving c to the left and then dividing everything by 2. We're going to leave, when we complete the square, before, maybe you made f of x 0 or something like that. Okay? We're just going to leave it as f of x. Okay? Because when we're done, we should have an alternative form of what we started with, and what we started with had f of x in it, right?
That's right.
Okay?
I thought it just made thunder.
All right. So completing the square, I'm not a meteorologist anymore. I don't know.
Did you say anymore? What do you mean anymore?
Yeah.
You say meteorologist?
No. All right, so completing the square, what do we do with that number right there?
Half it.
Half it, and then what?
You got me there.
Completing the square. Square, okay? So take half it gives me 3. Square it gives me 9, right? So now if I just added 9 to the right-hand side, This is no longer this up top, right? So what do I have to do over here? Add 9 over here, right?
Add 9 here.
Okay, so I'm going to add 9 this way. Is that still adding 9?
Yeah. I don't know why you did that way, but yeah.
Okay. Well, it's because I got this 13 halves over here that I need to add together. They're like terms. So I just wrote it as the same denominator. Now, the purpose of writing this way was so that this thing could be that's a perfect trinomial, which means it can be written as x minus, or whatever that sign is right there, and then half of that term. So x minus 3 squared. Now, if we're thinking about what we know about transformations, that minus 3 should tell me something about my vertex. Does that make sense?
Yep.
Okay. Now you know your vertex is at least at an x value of 3, right? It's been moved to the right 3 units. That's not something we knew from looking at 2x squared minus 12x plus 13. Okay. The left-hand side, though, is still kind of ugly, so I'm going to rewrite that as f of x over 2. Was it plus 5 halves? Okay. I'm going to try, so once we get to this point, we're trying to go back to, remember, we want to try to get f of x by itself. That's and trying to get us an alternative form of this. So I need to isolate that f of x. So you can either do you can multiply both sides by 2 first if you want to, or you can subtract your 5 halves from both sides if you want to. It doesn't matter. You want to multiply everything by 2?
Yes.
So it's going to be f of x plus 5 is equal now to 2 times x minus 3 squared, right? Okay. Now how do I solve for f of x? Okay, so f of x equals 2 times x minus 3 squared minus 5. Okay, so just kind of collecting some information here. You said first this thing was concave up. Second, we just found the vertex. The vertex is at that number, so 3, comma this number, negative 5. Does that make sense? Now visually think about this. Try and put this together in your head. 3, negative 5 is what quadrant?
I don't really know the quadrant, but
What?
it's just one.
Fourth quadrant.
Fourth quadrant.
Okay.
Wait, does it go 1, 2, 3, 4?
No, it goes counterclockwise.
Like a G.
Yes.
1, 2, 3, 4.
Yeah.
I
Okay, so we're in that quadrant. Okay. And it's concave up. Is that going to give you x-intercepts?
Yeah.
Yes. Okay. So that tells me I need to go further with this, find x-intercepts. Here's another thing. Every parabola, because the domain is all real numbers, is going to have a y-intercept. It's going to have a place where x is 0. Now, let's find the, just because we've already got to this stage here, let's find the x-intercepts first. Okay? Here's the idea. You've got two things you can do. You can either come up to this original one right here, and you can put 0 right there, and you can factor that thing, right?
Yeah.
You can. Now, here's my thought. Just think about this. If I'm going to do that, I'm going to tell you right now, I don't know if this is true or not, but I'm going to say, let's say the AC method does not work.
That always works.
Okay? No, AC doesn't always work.
Oh, yeah. Okay, yeah.
So what would always work? Quadratic formula. So you'd have to go opposite of b plus or minus square root of b squared minus 4ac over 2a, right? You have to do all that garbage. But where did that thing come from? Where did the opposite of b plus or minus the square root of b squared minus 4ac over 2a come from? We did it once this year.
Quadratic.
No, that is the quadratic. It came from taking this thing here, ax squared plus bx plus c equals 0, and completed the square on that thing. That's where the quadratic formula comes from. Okay? So, I've got a specific problem with A, B, and C here being 2, negative 12, and 13. But haven't I done most of completing the square?
Yeah.
Okay, so let's just keep going with this. Let's find the x-intercepts by making this thing go to 0. Okay, and the way this is set up, after we've completed the square, is that it generates your ability, or creates the ability for you to use the square root method to solve for x. Okay, what would I do first if I want to try to isolate x here?
Add 5.
Add 5 to both sides. Then what would you do?
Divide by 2.
Divide by 2. So I'm just going to do that all together at once. So 5 halves.
What was that, Charlie?
So we get 5 halves is equal to x minus 3 squared, right? How do I isolate x? Square root. So it'd be plus or minus root 5 over 2 equals x minus 3, right? Now what do?
Add 3.
Add 3. So I would end up with x equals 3 plus or minus radical 5 halves. That is exactly the same thing you would have found if you started back at the beginning and worked through the quadratic formula. Does that make sense? My thought is, once you've completed the square, you're already halfway there. Keep going. Okay, put a 0 in and solve for x. And it creates the square root method, which is what people, I think people gravitate towards that anyways. They want to do that with x squares. Okay, so now we've got our x-intercepts. So our x-intercepts are, what's the x value, or sorry, the y value for every x-intercept? 0, right? Now here's the thing. Do you know where radical 5 halves is on the? Not clear. Okay, so you're going to change that to a decimal. So we're looking at square root of 5 halves plus 3. So it gives me one of these is 4.58. And the other one is 1.41. And that's 1.42. Those are my x-intercepts. Is that okay?
Yeah.
All right. We should be able to justify that. What have we talked about? We did this when we did the projectile questions with the rockets and that kind of thing. How do your x-intercepts relate to your vertex? Or what line for your problem always goes through your vertex? Line of symmetry.
Whoa.
Okay. And then your vertices, or so your vertex goes or has a line of symmetry that passes through it. And then your x-intercepts are what in comparison to that? Equidistance. Good. Okay. So if I were to take 3 and subtract from it 4.58, or do just take the absolute value of 3 minus 4.58. I get 1.58, right? Okay. Take 3 minus 1.42. You get 1.58. Does that make sense? So that can be kind of a check. That's a relationship that should always work to make sure you've got the right x-intercepts and the right vertex. If they're not symmetric, then you don't have the right word. Okay. Let's see here. Then missing a y-intercept. If I'm looking at a y-intercept, which coordinate is 0 in every y-intercept? The x. Okay? So if x is 0, and you got some options here, and I just want to be thoughtful of this, I can come back to this line right here, and I can plug 0 in for x, right? Now think about what that would mean I'd have to do. I'd have to plug 0 in, subtract 3, get negative 3. And now I got order of operations. So square negative 3, you get 9, right? Double 9, you get 18, right? Minus 5, you get 13, right? 0, 13. There's your y-intercept. Now, is there a better place to find it?
Yes.
Where? Chuck!
Yeah.
What's the best place to find that 13? Where else do I see 13 up there? First line. Okay? So what we've got, so f of x equals 2 times the quantity x minus 3 squared minus 5 is exactly the same parabola as 2x squared minus 12x plus 13, right? So shouldn't they both have the same y-intercept, the same parabola? So if I go back up to the original and let x be 0 there, why would I let x be 0 there instead of in vertex form? Because doesn't that wipe away and that wipe away instantaneously? And now your y-intercept is just a constant, okay? And that's something we carry over to every polynomial. Every function that we see as a polynomial, your y-intercept is always 0, comma, whatever the constant is in the polynomial, the a sub 0 term from that kind of basic general format, okay? Does that make sense?
Yeah.
So that term will always be your y-intercept. So if we were to graph this stuff now, so this is the purpose of this. We now know we've got a vertex at 3, negative 5. Okay, we got a y-intercept at 4.58, one at 1.42, maybe there. Okay, we got a y-intercept up here. It's going to be not to scale, but my y-intercept is 0.13. And now, we can somewhat sketch that graph. My sketch kind of sucks. But obviously, the better scale your x and y axes are, the better the graph is. But that's the idea. We're trying to figure out the key points that exist on this graph that allow us to graph it. And we want key points that produce the entire graph, right? I want to make sure that I get enough on the left-hand side of the vertex and enough on the right-hand side of the vertex to get a real nice graph. The next thing they ask, and I'll always do this, what's the domain? All real numbers. It's polynomial, right? Okay. What's the range? -5 to infinity. Good. Okay. So that's the aspect right there, guys, that is going to come back to every single function that we deal with. Okay. And they're going to ask about that. Okay. So in your homework, they're going to ask, not every question is going to have a domain aspect to it, but periodically they're going to say, okay, now what's the domain of this thing? Okay. So those are things that we need to be able to pay attention to. All right, let's graph this thing. Should last class this. No, not really. But when we graph it in Desmos, okay, this is much more efficient than your TI-A 384. I'll show you how to do it on TI-A 384 tomorrow, or I guess Tuesday. But Desmos is so much quicker, okay? If I just type this in Desmos and then click on the graph, you can see some key points kind of pop up gray. 0.13, does that validate what we found? 1.419, comma 0. Vertex 3, -5. 4.581, comma 0, right? So those are all the things that we found algebraically. Okay? Something that they might do is provide you, so this, understand the overall purpose of what we just did was to generate points to graph something. And eventually that should be a quick process. Okay? So we can quickly graph the entire function. However, there will be times where they ask you, take this function, 2x squared minus 12x plus 13. Take the graph that you have right there and see if you can efficiently convert this 2x squared minus 12x plus 13 into our vertex form. So if I want to change this thing to vertex form, let's think about this. Vertex form is a times x minus h squared plus k, right? From this, I don't really know what h and k are, right? If I look at my graph, do I know what h and k are? So now I've got my h and k, right? So far, I've got a good portion of the 2x squared minus 12x plus 13. But if I were to FOIL that out right now, I would have x squared minus 9x, minus 6x plus 9 plus 5. If I think about that, that doesn't give me the 13, it gives me the negative 12x, it doesn't give me the 2x squared. It gives me a 1x squared, right? So what does that a have to be out front? Think about this. So this stuff here is going to be x squared minus, 6x plus 9 times that a plus my 5, right? I want that x squared right there to be a what up here?
2.
A 2. So if that's going to be the case, what does that number right there need to be?
A 2.
A 2. So this thing here is 2x minus 3 squared plus 5. Is that vertex form?
That is.
Was that much quicker to get vertex form than completing the square?
That's true.
Okay, so they might ask you to do that. But here's my thought. That process, remember, completing the square, finding the x-intercepts, y-intercepts, all that stuff, was to generate the graph. I think this type of question kind of defeats the purpose of learning this stuff. And they'll give you things like this and ask you to do it just to help us understand what's going on, get exposure to this type of stuff. But this is kind of working backwards, right? Okay, this is giving me the graph and now asking what was the vertex form that came from that. If you can do that, then hopefully maybe generating the order pairs and stuff like that is easier for you. I'll show you on Tuesday how to do that, your tally 83 or 84. It's a pain in the butt, okay, especially when we start getting large numbers for vertices and stuff like that. You guys remember x equals the opposite of b over 2a?
Yeah.
Okay.
Is that coming back?
Yeah, it's coming back because that number, opposite of b over 2a, that is that number right there. It's the x-coordinate of your vertex, right?
Yes.
Okay, so if it's the x-coordinate of your vertex, it gives you a way, instead of maybe completing the square, it gives you an alternative way to find that very quickly. And if I know what the x-coordinate of my vertex is, and I know the original 2x squared minus 12x plus 13, I should be able to put that negative 3 in there, put that negative 3 in for x squared up there in the top line, and it'll spit back the 5 that you need for your y vertex, or your y coordinate. Okay? So we'll do that on Monday, just an alternative approach instead of completing the square. And those are things, guys, then when we get on a test, if I've got 3, 4 different ways of approaching this, and the directions are just say, hey, graph this, find me these points. Does it say which way you got to do it? No. Okay. My hope is if you know 2, 3, 4 different ways, you're able to decipher which way is quicker. Okay. And maybe you got 2, 3, 4 different ways. You can say, oh, I'm going to do it this way, and we'll check it the second way. Okay. So those are that's the plan for Tuesday. Yes.
Can you show me on my calculator sometime how to cube root? Because I have no clue.
Math. I'm going to go down to this calculator here.
No.
If I were to cube root something, I'm just going to raise it to the 1/3 power.
Okay, that's what I've
That's
been doing.
easier.
I don't like doing that.
Is it this calculator?
No, that's why I had to grab a red one. Remember?
Well, give me your calculator. You say he cubed?
Yeah, he said he cubed my mom's root.
Oh, that's on film. That's awesome.